Recording. Okay. Let me get to the slide. And to avoid distractions, I can. Okay. How does it look? Can you see the slide full screen? I hope so. Okay, perfect. All right. Good morning, everybody. Once again, let's get started. We can just pick it up where we left off. So we looked at a truth table with 3 inputs in the last class. And we looked at all possible combinations of these 3 inputs. And there are 8 possible combinations, right? If we had 4 inputs, there would be 16 possible combinations. And we found a way to express any Boolean function that is represented by 3 input combinations in a format that is compatible with Boolean algebra, for example. So something that we could handle with Boolean algebra later on. This is a very powerful approach because it's universal in a way that you don't have to manually think about implementing this function every time. You could just follow a rule and it will work every time. That is a big deal. And here in this particular example, we started with a function that was like randomly chosen for no reason. But today, after this discussion, a couple of slides of discussion, I will show you some specific real life example that will hopefully make a lot of sense. And that will also be related to your lab assignment that I uploaded. That's the reason why we are at the right stage to talk about the other example. And, just to get ahead of ourselves, it's going to be adder. We'll talk about adder circuit today after this. So long story short, very quick recap. This was a function that we randomly chose that, hey, assume that for so-and-so combinations, we're going to have 1 at the output. And for all the other combination, you'll have 0. Now, the strategy that we take to incorporate this function is just look at the outputs that are 1. Okay, just the output. And by the way, in case you're wondering, we have an extra column with if prime, which is the complement of the function that we're trying to implement. And there is a reason why I have this extra column, or which I will talk about, but for now, just ignore it. For now, ignore it. Look at the outputs that are 1. And we are just going to see which combinations of ABC will lead to this 1 output. So let's take the first row. And whenever you see 0, it represents the complementary version of the input. So if you have 0, 1, 1, you can have a 1 output. So I'm going to write it this way. A bar, because you have 0 here. Sorry. Sorry, give me a second. So I'm trying to incorporate this one. And this is the first row I've taken. We'll start with A bar, B, C. A bar because you have 0 here. And then the others are 1. Or if you have this other row, which is represented by A, B bar, C bar, or B prime, C prime, because you have zeros here. And then you have the third row. That means you have A, B prime, C. Then you have fourth option, which is A, B, C prime. And finally, you have the other option, which is A, B, C, because all these 3 inputs are 1. Okay. Now, your output will be 1 if this happens, or this happens, or this happens, or this happens, or this happens. Basically, I'm spelling out the function, as you can see. So this is our logic function, Boolean logic function. So this function, if you take the other way around, if you try to come up with the truth table by plugging in zeros and ones in place of ABC, you'll end up with this truth table. You can test it, and it's a good idea to test it at least at home, just to be sure, right? Just plug in zeros and ones in here in this function and see whether it leads to this functional outcome. Okay, now what you saw is how you can implement the Boolean expression for this truth table, but you haven't seen the simplification. So after you have this Boolean expression, you can go through some Boolean steps that we saw, optimization step in the last class, and simplify it further, as you see. I mean, I'm not getting into the detail of it here, but I mean, you can see this simple approach. Just take AB as common, and you're going to end up with um, C prime plus C, which is basically 1. So you'll have AB left. And then between AB prime and AB, if you take A as common, you'll be left with B prime plus B, which is again 1. So you'll just have A here. So that's why the first term and then just A. All right. And then you could, if you remember, you have A and A prime here with some other variable. You could basically just get rid of this A prime using a theorem that we saw in the last class. So please review that. And the point is, once you have a complicated Boolean expression, you can always go through some steps to simplify it to get something that is easier and more efficient in incorporate. Okay, just imagine if I tried to just randomly jump in from this expression that we got and try to make a circuit out of it. I would have needed, let's try to calculate it manually. Let's do it together. I know it's not the most ideal when it's virtual, but we can still give it a shot. You can try to think about the answer yourself. So imagine to implement this one, we would need a 3-input AND gate. And then for the other one, another 3-input NAND gate. For the other one, another 3-input NAND gate. For the other one, another. So I'm running out of space. I mean to draw 3-input NAND gate. And for the other one, so you need actually 5 3-input AND gates. And then you have to take an OR for all of this AND operations. So basically, you need an OR gate with all these inputs, 1, 2, 3, 4, 5, and this is your functional output. Obviously, it doesn't look like a complex solution, like compact solution, right? Compare that to this simplified expression where you have A plus BC only. So all you need is, for BC, you need a 2-input AND gate, and then you need to take an OR with A, and you get your functional output. So that's why Boolean simplification is so important, right? Without simplification, yes, you arrive at at an approach that gives you Boolean expression from any logical Boolean truth table, but you still have to care about simplification. All right, now let's take a look at a different approach to getting this functional output, Boolean output, which is honestly, I think, even is going to lead to even more complicated expression, but there are reasons why people still talk about it, and we will talk about it here. So what you saw first was a sum of product expression. So here is why it was named so. You eventually take a sum, not this one. I meant to use the other row, this row, because that's where we landed, right? You take the sum of products. So SOP, sum of product. And there is another way to achieve this function that is called product of sum. And as you see here, apparently you end up taking a product of some terms. So you have some terms here, and you will have to take products like we discussed in the last lecture. But how do you generate this functional output? So for this one, you look at the zeros, not the ones. All right, you will look at the zeros, not the ones, remember. So look at the zeros, and then basically wherever you have 0, you have the regular input, and wherever you have 1, you have to take prime. So basically exactly the opposite to what you are doing. Previously, wherever there was 0, you had to take prime to make it 1. But here, for OR operations, you basically take 0 to be corresponding to your functional inputs. So the first combination has 0, 0, 0. So you write A, B, C, but instead of AND, these are going to be OR combination. For the second row, you have 0, 0, 1. So I like the first 0 and the second 0, which is A plus B, but I don't like 1, so I'm going to write C prime here. So you get the second term. And the third term would be, you have 0 here, so you have A, then you have 1, so you have to write B prime, and then you have 0 again, so it's C. So you end up with 3 different terms. And now you have to take product or AND. Basically, this product represents AND. So this is the expression that you end up with this approach. And obviously, it doesn't look anything similar to the one that we ended up with. However, we haven't simplified, as you can imagine. To simplify it further, we'll first have to multiply this, basically, and then multiply this with the rest, and then simplify. So it requires even more steps, Boolean algebra steps, than you saw in the first approach. So if I ask you to pick one, also there are questions. Thank you for asking questions. So if supposed to be all possible permutations of A, B, C, that's a good question. So apparently, for all possible combinations, we have these rows. Notice, this pretty much covers all possible combinations. But when we generate the functional output if, we only take the ones, because you are looking at when will this function give you 1 for these combinations. For all other combinations, it's going to be giving you 0. So this expression will automatically generate 1 when these rows appear, because that's how we generated them. Okay. For all the other rows, it will automatically generate 0. So it's essentially covering all possible combinations, right? As the question goes. I hope I answered the question, but if not, please, put a follow-up comment. All right. So, by the way, I hope you now can see that there are 2 ways to generate the same function. Just look at the ones and go for this sum of product option, or just look at the 0 and go for the product of sum option and eventually reduce it down to a simplified version. As you can see, they both lead to the same simplified version, apparently, but you need more steps for this one. Can anybody help me understand why on earth somebody will possibly consider using this approach? And I can give you an example, by the way. So I want any one of you to possibly just try and give me an example. When will it make sense to not use this at all, but to use this other approach? Can anybody tell me? You can try, please. And you can be wrong. And I think it's better to be wrong, honestly, because that's when we learn new things. Okay. Anyone wants to put something on the chat?
Yeah, I'll try.
Yes, please.
So when you're trying to find multiple outputs, it might be a little bit more difficult to come up with the top one, but the second one has like a pattern to it that can be easily reproducible.
Yes, you're right. That's true. And to be honest, both of them have patterns. Like, you are heading in the right direction. Both of them have patterns. So that's not really the answer I'm looking for. But thank you for trying. You are partially correct. And also there is another comment about security. And also when there are small, exactly. Thank you so much for that answer. Uh, so when there are a small amount of 0 for our function, and apparently, let me make an extreme example of it. What if these other 2 entries were also 1? Okay. That means you just need to take care of 1 row if you go through this approach. All you have to do is write A plus B plus C, and that's your function. Super simple function. Now, compare that with the other approach, which seemed basically simpler. But now for this other approach, which is, let me use a different color here. This other approach, you will have to go through all these rows, write all these terms, and then simplify only to arrive at this solution, A plus B plus C, which you are arriving with just one shot with this other approach, right? So that's why both of them have value, but not all of them will be like, not both of them will be equally suitable for your scenarios. All right. So I hope that makes sense. All right. So let's move to the next slide. We are going to look at 2 very important terminologies here. One is called min term and the other one is max term. So if you have 3 inputs, A, B, and C, you can have 8 possible combinations, as I keep saying all the time. Apparently, these are exclusive. Like, these constitute all possibilities with 3 inputs. There cannot be any other possibilities beyond this, right? So why don't we just come up with names for all these combinations. So there are two possibilities with these three inputs. You can take the product or you can take the sum, as you must have seen. So when you take the product, apparently for zeros, you have prime. For ones, you just have unprimed version of the variable. So A prime, B prime, C prime represents 0, 0, 0, and A prime, B prime, C represents 0, 0, 1, and so on. So all these combinations that you see here, and as there was a question previously, this primed and unprimed variants represent all possible combinations of literals with ABC. So if you could do ABC, great, you have it. You could do A prime, B prime, C prime, sure, you have it. You could do A prime, B, C, you have it somewhere. You'll find it, right? So any possibility that you can think of with A, B, and C and their primes are all available in these 8 rows, okay, in product form. So this essentially constitute all possible product forms for ABC. And these are called min terms. We represent them with this lowercase m. And also notice M0 is the standard. Where if I just ask you to write M0, it's always going to be the 0th row. If you organize them in increasing format, as you see, as the number is going up from low to high, 0 to triple one, right? As you see in binary. So apparently this is the lowest one. So this is M0, 0th min term. And the next one is M1 and M2 and so on. Finally, you get M7 because triple one represents 7 in decimal, right? Triple one in binary represents 7 in decimal. Okay. I hope that makes sense. I'm happy to stop and revisit if you have questions. Otherwise, I'm assuming that you understood it. Okay, we can do something similar for the max term, which is another terminology we're going to use, and we will represent them with uppercase M. And instead of products, we are going to just take sum. And remember, our strategy for these terms would be to take the function, to take the inputs as is whenever you have zeros. So for 0, 0, 0, you have A plus B plus C. For 1, 1, 1, you have A prime plus B prime plus C prime. Okay. And by the way, I keep interchanging this symbol with this other prime, as you understand that these are essentially the same. So please don't get confused. Sometimes in some slides I have this because it depends on which textbook I took them from, right? Or which sources I took them from. That's why. Okay, so this represent all possible or combinations with A, B, and C. This represents all possible and combinations with A, B, and C. So you have a list of min terms, you have a list of max terms, and we are going to do something interesting with them together right now. Let's move to the next slide. Okay, this is our chart again for reference. I am going to now use the function that we came up with together and represent that in summation in a format of min terms and max terms. So apparently you could just use this chart and find which min term this AND operation represents. So A prime BC, let's try to find A prime BC. This is A prime BC, as you see. It represents M3, min term 3. So I'm going to just look at these AND operations, find it from this chart, and replace that with the corresponding min term value. Okay. So apparently, you could express this function instead of using ABC, AB prime, like spelling them out, you could just represent them with a list of min terms. Okay, this is a much simpler representation, and there are other reasons. We are not doing anything for, just for the sake of it, honestly. And I'm only teaching you things that we will eventually use, by the way, right? So it's not just there is just another way to represent it. There are other ways to represent it because those ways will possibly make things easier moving forward. So instead of spelling out all these terminologies, we could use these min terms and max terms. And remember, M5 is always going to be this one. You cannot just randomly name anything M5, okay? Because these are organized in increasing order, as you see, corresponding to this binary combination, 101. 101 represents 5, so this min term represents 101, essentially. Okay. So does that make sense, folks? Should you remember all of the terms? No. Throughout the course, you don't have to memorize anything. That's a general comment. Thank you for asking that question. It's a very important one. So don't worry about memorizing it. But honestly, it will be like, for example, when I try to draw something, I'm not basically memorizing 0 0 0 0 0 0 1 0 1 0 0 1 1 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Did I memorize it? No, I didn't. Basically, I'm just writing it logically in increasing order. So what is the minimum possible number you can come up with three inputs? 0 0 0. What is the next, you know, number in line? It would be just 1, as you can see. What is the next in line? It is going to be 2 in decimal, which is 0 1 0 in binary. And what is the next one? 3 in decimal, which is 0 1 1 in binary, and so on, right? So when I just logically organize them in this chart, you end up with this sequence, and then you just take the corresponding number 0 1 2 3 4 5 6 7. Simple. So you can easily regenerate this chart by yourself at home, and I recommend try that. Just basically take a blank piece of paper and try to regenerate this from logic, not memory. All right. I hope that answers the question. Should you remember? No, you don't. Does it only work with 3 variables? That's a great question. I was eventually going to answer that after the last slide. So I'm going to answer that after the last slide. Thank you for asking that question. All right. All right. So, by the way, I hope we understand this now, but there is one other line here which we haven't talked about, which I'm going to do that right now. This is basically a simplified expression of the same line that you saw. Oftentimes, we just represent that as sum of min terms and just use the numbers 3, 4, 5, 6, 7. So 3, 4, 5, 6, 7. Just another easier way to express. So imagine, I mean, let's do the other way around. Forget about this function. I'm going to give you a function like this, a prime b c plus abc. Let's try to make the midterm expression for this function. Let's find a prime bc first. Where is a prime bc? This is a prime bc, as you see. So this is m3. So I'll have m3, and abc is essentially m7. m3 plus m7. So I can also write it in a fancy way to show summation of m and 3 and 7. Okay? Oh, how about the other way around? If I give you an expression that looks like this, m6, 7, say, and I ask you to find the function. The function would be, let's see what is m6. m6 is abc prime, abc prime, and then plus, that's what the sum represents. m7, which is abc, abc. See, it's a much quicker way to represent and much easier way to express these functions rather than just spelling out everything. Are we all good? And I'm coming to the point whether or not it's just for 3 variables. Okay, a short answer is no. It can be extended to any number of variables. Okay, we'll do it like after this slide, literally. Okay, so max term expansion, instead of, like, as you can imagine, if we do something with min terms, we could do something similar with max term as well. And this is pretty much, this is the expression that we got together. You just represent them in terms of max term, like we did for min term. So what is a plus b plus c? A plus b plus c is the very first max term, which is m0. And then a plus b plus c prime, which is a plus b plus c prime, is m1, and then m2. And apparently you have all these max terms multiplied together, which is like AND operation. So you take the end of all these max terms. So in max term format, they look, even simpler, as you can see. But notice the pattern here. I don't know if you have seen that, but maybe I will use the next slide as well to represent. Before I get to the next slide, an easier format, or like another format to represent that, is to show product of max terms and then just spell out the numbers 0, 1, 2. Okay, now if I give you a function that has sum of max term with 3 and 6, say, I'm first going to look for what is a max term 3. It is going to be a plus b prime plus c prime. So let's do it. A plus b prime plus c prime. Okay, and then 6. What is 6? This is max term 6. So it's going to be a prime plus b prime plus c. And then I'll have to take product. There you go. That's your function. Yes, you can always simplify it later on, but at least you arrive at a functional solution that works. I hope that makes sense. And by the way, if you're wondering, will I have to go back to the chart to find this every time? No. Easier way. Let me show you. Uh, say what is what are the max terms here? 0, 1, and 2. What is the binary format? Just treat them like decimal numbers, by the way, because that's what they are. 2 is decimal in 3 bits. So what is 2 represented as in binary? 0, 1, 0. So basically, that's your corresponding max term row, 0, 1, 0. And all you have to do is just use this and express that in using the inputs, which is A, B, and C. So for 0, you have A. For 1, you have B prime. For 0, you have C again. So there you go. A plus B prime plus C. And notice A plus B prime plus C is your second max term. If you're trying to look for min term with 2, 0, 1, 0, you don't you have to do the opposite. For 0, you have prime. For 1, you have unprimed. And for 0, again, you have prime. So A prime, B, C prime. So notice A prime, B, C prime is your M2. I hope that makes sense. And please practice it at home. The more you practice, honestly, the more it will be like breathing, honestly, at some point. Because this is so universal that you cannot get away with it ever if you're in the digital electronics universe. All right, so I'm gonna get to the last slide of this particular lecture, and then I'll comment on the versatility of this approach. So notice, for the same function, if you use min terms, you end up with this expression. If you use max term, you end up with this other expression. Can anybody notice anything interesting? Interesting pattern here? Like Sherlock Holmes? Any Sherlock Holmes in the class today? Any clue? Well, how many numbers can you get with 3 digits? You can get 8 numbers starting from 0 to 7. And notice in the min terms, you have 3, 4, 5, 6, 7. If you try to express that in max term, you have the rest of them. Okay. So whatever you didn't use for min term, you have to use for max term. And vice versa, by the way. So if I give you the min term expression for a function, you can easily come up with the max term expression. Like 3, 4, 5, 6, 7 have been used. Sure. And I ask you to create the max term expression. Here it is. Max term would be whatever was not there. You don't have 0, 1, and 2. So there you go. So given one, you can easily get the other. And as you can see, this could be very powerful. This could be an interesting homework problem as well. But the reason why I didn't upload the homework, because I realized I added a problem with this and I didn't cover this in class. So I didn't want to confuse you. So now you're ready to work on the homework, which I'll upload. But the lab is already uploaded. The homework will be after today's class. Okay, so I will stop here, and I will also point out how to kind of take it to the next level. So imagine if I had 4 inputs, A, B, C, D. What will change here, folks? Instead of 7, you'll go all the way up to 15, meaning you have 16 possible numbers. So you have 16 possible combinations here. So everything else will be exactly the same as I just discussed. Okay, all the approaches will be the same. It will just take more manual labor to just do this the way we did, and also will be a nightmare to explain in class within a slide, because we'll run out of space. That's why we always choose 3 inputs to show how this works. But it is universal. It could be extended to any number of inputs. The only difference is your rows will keep getting more and more. Okay, but the min term, max term expressions, that the rules that I talked about, they remain exactly the same. Okay, I will, maybe that gives me an idea to add, add an extra problem as a voluntary solution. I will add it actually for you to try doing this with, say, 4 inputs, and that will be fun, right? All I have to do is just update this table for 4 inputs. That's all. And then you could just get the function out of it. Okay. So did I answer all the questions, and are we in good shape so far? Anyone? Okay, I don't hear anything, and I hope that's a good thing. How do we know how many row numbers there are for a different number of inputs? That's a great question again. So basically, it comes from our combination and permutation classes. So imagine if you have, easy way to remember, if you have three inputs, you have 2 raised to 3 possible combinations. If you have n inputs, you have 2 raised to n possible combination. Okay, so for example, for 4 inputs, you have 2 raised to 4, which is 16. For 5 inputs, you have 2 raised to 5, which is 32, and so on. Okay, this comes from, basically, if you have taken combination and permutation classes, they typically teach you how to, like with coin tossing, for example, right? How many possible combinations can you have with coin tossing, for example? And you basically arrive at the same answer. If you have n number of tries, you have 2 raised to n possibilities. Does that answer your question, William? All right. All right. Sure. Thank you. So let's move to the next lecture. And you might be wondering, hey, will we be able to finish that? Yes. Here is why. Because this is basically shaped to be an auxiliary lecture for the one that we just completed. And this will be a bridge towards your lab assignments. And here is how. We will take a look at specifically 2 things here, 2 examples. One is a multiplexer and the other one is adder. Okay, I'll show you how that works. So a multiplexer is a universally used Boolean logic circuit, like say AND and OR, but it's not a fundamental logic circuit. It is made with other logic, as you will see. And you will work on this in the lab. So I don't need to get into too much detail here. It will make a lot of sense when you go through the lab. Okay. So this is a multiplexer circuit. What it does is it uses a select signal, and based on the select signal, it chooses the input. So if the select signal is 0, it will choose this first input and take it to the output. So your output will be A if select is 0. If select is 1, it will take the second input and bring it to the output. So your output will be A when your select is 0. Your output will be B when your select is 1. Okay, that's pretty much what it is. And I'll tell you why this could be very powerful. But before that, let's take a look at the truth table. Okay, you have, how many inputs do you have? My question. Okay, first of all, these 2 bits are inputs, A and B. And also you have a third input, which is the select signal, which can also be 0 or 1. So you have 3 inputs, 1, 2, 3. So with 3 inputs, you arrive with this universal truth table, as we have been using it for a while, right? Okay, and let's take a look at the output logically. I mean, without going through the math and everything. Okay, as long as your select signal is 0, whatever you have here should be at the output. So your output should be exactly what A is. And A, as you see, if A is 0011, your output will be 0011. So your output follows A. All right. Now, if the select signal is 1, whatever you have in B, your output should follow. And that's exactly what you get here, as you see. Okay, I hope that makes sense. So you can always come up with this truth table manually. And this is the output for your multiplexer. I hope that makes sense to you. And just take a look at the truth table, and always take a truth table and try to make sense of it by yourself, and it will help a lot. Okay, so notice now we have an output, and all we have to do to express it in a functional format is to look at the ones or zeros. And I'm choosing to do 1 because you see you have 4 ones and 4 zeros. They're equal. So there is no advantage going to the other route. I'm just going to take, product of, I'm going to take sum of product approach. Okay, so I'm going to look for ones only. So for the first one, I will do S prime, A, B prime. For the second one, I will do S prime, A, B. For the third one, I will do S, A prime, B. For the fourth one, I will do S, A, B. Okay. And now, once you have it, you can try to simplify it further if you can. And you can definitely, I mean, it's part of the lab. So you do it. And then you express that in a Boolean format with AND gates and OR gates. And there you go. You get a multiplexer out of it. Okay. This is what you're going to implement in the first lab. So I don't have to talk too much about it because you will be working on it. And after you go through the lab, if you have questions, please ask me. So this is an introduction to 2:1 marks. Why is it called so? Uh, so by the way, there is a question. So for this lab, you don't have to buy or collect any lab supplies, but you don't have to buy anything ever. We already organized everything and it's ready for you to pick up, but we will get there. The first lab is just simulation and software and your pen and pencil. But the next ones, we'll let you know when you need to collect those things from the parts shop. Okay, thank you for the question. All right, so this is called a 2:1 mux because you have two inputs and you have to select between the two inputs and choose an output. So you're basically choosing between two and picking one. I want to show you one interesting things here. Lab sections. That's a good question. So I see another question here. The lab sections posted already. So as I discussed in the class, in the last class, I think this lab, I'm taking a different route. Without making you go physically to a lab location, I'm trying to provide a detailed tutorial which you can follow along and do it yourself. And I've tried that in my other courses in the past. They worked like charm. And I don't take my word for it. If it doesn't work, I will change it. No worries. Okay. We are doing an experiment together. If the experiment fails, no worries, you'll not lose out anything. I hope that we could always arrange a session if necessary later on, like maybe next week or so. If you feel like, hey, no, I still need to be in a physical lab with the TAs to work on things. So give it a shot. I uploaded a 20-minute video. The TA was kind enough to prepare it in advance for us. So you can listen to this 20-minute stuff rather than just sitting somewhere for 2 hours or an hour max, for example, which could be annoying. And then just follow along. It will make a lot of sense and you'll feel more independence. You'll feel more empowered, I think, because when you're doing it yourself, just between you and the tutorial, I think it gives more confidence, at least for me. So try it out. If you don't like it, we'll change it. Okay. I hope that answers the question. So as of now, there are no lab sections yet. I will try to create these sections before the project because the project will probably be in groups and there are some logistic stuff that we are taking care of. Okay, now this is the 2:1 marks. Oftentimes it's also mentioned as 2x1. It's all the same, you know, basically the way you represent it. Our lapsing, okay, all right. So let's move to the next one. Another example, this is taken from a different source, as you see, this is basically a screenshot. 4:1 marks, it's similar to represent four combinations. You cannot just use one select signal because that select signal will only give you 0 or 1. But then if it is 0, you choose 1. If it is 1, you choose the other. How about the other two? You don't have any way to choose the other two, right, with the select signal. What you do is you incorporate an additional select signal. So you have two select signals and 2 gives you four combinations, like 2 raised to 2, four combinations. So you have 0, 0, 0, 1, 1, 0, 1, 1. So for 0, 0, you take this input to the output. For 0, 1, you take this input to the output, and so on. So this is called a 4x1 mux or 4:1 mux. Okay. And this is the truth table for 4:1 mux. And you could keep going. You could, do 8:1 mux and so on in power of 2. Okay. These mux circuits are heavily used in digital electronics for many reasons, but I'll give you one. Those of you who have coded in C or any other language, you must have used if else, right? If else conditions. If this happens, do that. If something else happens, do something else. If this other thing happens, do that other thing, right? So this is essentially your if else condition in hardware. If you have this, do this. I'm just spelling it out and drawing it on top of it, as you can see. If the other option occurs, do the other thing. So basically, this mux is nothing but a physical representation of if else condition. Now, if you have just two conditions, this 2:1 mux will work. But if you have more, you need to get to the 4:1. And if you have even more, you need to get to the 8:1, and so on. They require more complicated hardware implementation, but you can still do it. Okay. So work on the lab. Hopefully that will give you a better sense of the marks. Now let's move on to the addition. We have already seen that. So I don't have to spend too much time here. When you do addition in binary, I hope you remember this. Let's take and add these two numbers. So this is your first number. This is your second number. Notice when you add, you don't add the whole number with the other, right away. You take one bit at a time and then add and then get to the next bit and then get to the next bit and so on. You go from right to left, right? Least significant to most significant bit. This is an observation. So when you add these two bits, after adding 1 and 1, you get 1, 0, as you can remember. You just put 0 here and take the other one to the next position. We call it a carry, okay? And then you keep doing it over and over again. We call it a carry. So notice when you're trying to do, when I design an adder circuit, I'm concerned with one bit adder, one bit. I'm trying to, what do I mean by that? I'm doing bitwise add, every bit, one bit at a time, okay? To do so, how many inputs do I need? I need one bit coming from one of the numbers. I need another bit coming from the second number. So you need one input, which is A, for example, another input, which is B, but remember, this is not the end. Simply, this was the first input. There was no carry coming in. But the next one will have a carry. The carry will come from here. And then there will be a bit coming from one of the numbers, another bit coming from the other number, and then there will be a carry input coming from the previous stage. There may or may not be a carry. If there is no carry, it will still be 0. But I have to represent that somehow, right? To represent the carry, I need an extra input. So how many inputs do I need to do a bitwise add? I need A to represent a bit coming from one of the numbers. I need B to represent a bit coming from the second number. I need carry in to represent a possible carry coming from the previous stage, if any, but I still need an input to represent whether there is or not, right? So I need three inputs and I need what? So after you do the sum, notice you started with two 4-bit numbers. So you end up with a 4-bit sum. Okay, your sum will also have to be 4-bit. But then you have an extra carry that you can represent with your sum. Okay, so to represent whether there is a carry or not, you need an extra output. So your output is not just sum, but also carry. So just remember this stage that we did. When you added these two bits, you ended up with 1, 0. You could only keep 0 here, which is the sum. But what? How about the 1? That 1 will have to be represented as carry out and fed to the next stage. Okay, so for this operation, you don't have just one functional output, you have two functional outputs. Okay, you have sum and carry. This is a unique Boolean logic that you're seeing. Typically, you're used to looking at multiple inputs, one output, right? Here, you're looking at multiple inputs, multiple outputs, at least two outputs, sum and carry. It's interesting, but not too, not too crazy, I think. Okay, so when we create the truth table, you have combinations of inputs and then you have combinations of sum and carry, which both of them are output. You have output 1 and output 2. So I have to come up with two expressions, two Boolean expressions, one representing sum, one representing carry. Okay. Now I want to, I mean, I don't have to tell you again that once you have this ABC, which is 3 input combinations, I have our universal truth table ready for us. Okay, we just have to go through them and create the other two columns. And I want to show you how to manually do it. Okay, let's do it. So imagine, since you have 3 inputs, 0, 0, 0, there could be a situation where you have 3 zeros. If you have 3 zeros, if you add them, you're always going to get 0 as a sum. And the carry will always be 0. So let's see whether we have any input like this. Yes, we just have one input like this. Your sum is 0, your carry is 0. Done. Let's go to the second combination, 0, 0, 1. Okay, so here you just have 1. So basically your sum is going to be 1 and there is no carry. By the way, will it change if this 0, 0, 1 becomes 0, 1, 0 or 1, 0, 0? It shouldn't matter. As long as there is just 1, 1 and 2 zeros, you are always going to get a sum of 1, if you think about it. And your carry is always going to be 0. So let's look for the case where you have 2 zeros and 1, 1. 2 zeros, 1, 1. Let's see where else. 2 zeros and 1, 1. There you go. And all of these will have a sum of 1. And your carry should be 0. See, I could just manually fill it up. Finally, not finally, there are two combinations left. So I know we are out of time. So what I'm going to do, since we are virtual, if you have to drop off for another class, please feel free. I'm still gonna take 5 more minutes to finish it up. I don't want to just break it for 5 minutes and then upload the recording. Okay. Sorry about that. Like for the initial mishap with the Zoom link, we had to start a little bit later, but we will be done in 5 minutes. Okay. Please give me 5 minutes. So this one, the second combination, you have two ones. When you add them up, you get 1 0. That means the 0 will be left as sum and 1 will be given as carry. Okay. So whenever you have two ones, doesn't matter which position, is it 0 1 1 or 1 1 0 or 0 like 1 0 1, doesn't matter. As long as there are two ones, you're going to get a sum of 0 and carry of 1. Okay. So let's look for these combinations. You have two ones here, you have two ones here, two ones here, and I think that's it. So you have sum of 0 and carry of 1, like we noticed. Finally, there is one combination left where you have triple one. For triple one, you end up with 1 1 because triple one is going to give you 3, which is represented as 1 1. Okay. So 1 is your sum, 1 is your carry. So that's the combination you get. And by the way, I don't have to tell you, once I give you this sum expression, you can now go ahead and let's go ahead actually. This is your sum expression. And I'm going to only look at the ones, 4 ones. So let's create this expression together. You have A prime, B prime, C. And by the way, C is represented as CI, which represent carry input because you also need a carry output. So if you just use C, there will be a combination. Is it input or output, right? So we have to use CI for input, CO for output. So that's why you see for this one, you have A prime. Let me show you. A prime, B prime, Ci. For the other one, you have A prime, B, Ci prime, and so on. You'll have other two combinations, right? 4. And this is the combination you end up with. You can try it at home or you'll do it in the lab actually. And basically this could also be represented in form of A XOR B XOR C. I'll let you think about it and then I'll talk about it in the next class as well, but it's not important. As long as you have this expression, you can get the circuit, but this also represents a 3 input XOR. Okay, we'll talk about it. And if you do the same for carry, look at the ones and try to incorporate that in Boolean function, you end up with this other expression. Try it out at home because you'll be working on it in the lab anyways. Okay. And that's what I needed to cover today. One thing that if you are curious, how we are basically taking one bit at a time, but in hardware, how do we handle adding the full number? So what you're looking at here is a building block, like just one block. So when you add these 2 digits, this is the circuit you need. But for the other 2 digits, you need a similar circuit like this. So this circuit will provide input to the other. Can anybody guess which input will go from one of these circuits to the next one? Which input? Will it be sum? No, you don't feed the sum to the next level. You feed the carry to the next level, okay? So your carry output will be fed to the next level and to the next level and so on. So that's what you see here. It's not part of this syllabus, by the way. We basically look at it in the in 433. There is a project that students do. It's called ripple carry adder design. So you have an adder. The carry out of this adder is the carry in for the next step and the next step and so on. Okay, just in case you are curious, I had this figure handy. So take a look at it at home. You'll work on it in the lab. So hopefully we'll be in good shape. All right. And that's 5 minutes. Thank you for giving me the additional time. And thank you for your flexibility again for, in joining the virtual class. All right. It was very encouraging for me to see so many participants. Thank you all. Take care. All right. Looks like the lab has video set to private. I'll change it right away. Thank you for pointing it out. Thank you. Oh, so there are some questions. Yes. So yes, our first exam. This is a great question. I will post an announcement next week about the first exam, the midterm exam and everything. Thank you for, pointing it out. All right. Next week. So keep an eye out for an announcement next week about the exam schedule. I'm gonna, make sure to upload that. All right. Thank you, everybody. I'll see you in the next class in person. Bye.